Developing recursive solutions to the problems that you're trying to solve isn't a skill that comes naturally to many people. And I know this because it didn't come naturally to me. But using one cool trick that we're going to reveal in today's lesson will hopefully give you a light bulb moment the same way that it did me in reframing the way that you think about these problems and giving you a much more approachable way to go about solving recursive challenges. So let's get started by thinking about recursive structures and what we mean by this. Well, we're talking about in this sequence the simplest recursive data structure we can imagine, which is a singly linked list. And we can imagine a singly linked list where each of our node objects has some values associated with them. So say 110 and 210, just some numbers out of the blue, and then our lists are terminated with none, not node, none. Each of these are node objects. So I might label these as my haystack. We're going to be implementing a search algorithm here, and we're going to be searching in a haystack. So this will be our haystack of node objects. All right, so this is our linked list. Okay, and if we're going to get some practice thinking about a recursive algorithm, we need some problem to solve. So we're going to be asking, does this list include 210? Does any node in this list include a value such as 210 in it, right? And if we want to come up with a recursive solution to this problem, we're going to need to think a little bit differently than we would if we were thinking imperatively about this. And so before we get into a recursive solution, let's think about if we were trying to think of an imperative solution to this problem. And when I use the word imperative, I tend to mean loops, right? And this is what it classically means. So imperative. We're thinking about looping through a problem. So we would start at the front, and for each node in my list, or check and see whether or not it's what I'm looking for, and then we're done with it, right? So in an imperative solution to a problem, often we think about like, okay, we're going to start at the very front, and we're going to keep looping until we reach the end. And if in the middle of that process we find what we're looking for, we'll go ahead and return. If we get all the way to the end, and then at the very last step would be, well, we didn't find it, right? And so this is a very natural way of describing and coming up with a solution to a problem, often for many people. With recursion, the trick that we're going to learn is to actually flip the script on that process entirely and try and think about, well, how do we solve this from the back of our problem, or from the end of our problem, from the simplest type of problem we can imagine, and work our way back out of it. So let's imagine what this might look like. First, our goal is to have a function that has a signature that looks something like this. Includes is going to be the name of our function, and we're going to have two parameters, right? A haystack, that's what we're searching through. That's going to be our list of nodes, and a needle, right? So we're looking for a needle in a haystack, and this should return a Boolean, right? True, false. And what we're writing out here is very much just pseudocode, thinking about this problem in a very abstract, hand-wavy sense, all right? So what is the simplest problem we could solve here? Like, what is the easiest haystack we could imagine to work through to know whether or not we found the needle that we're looking for? Well, the empty list, right? When there's nothing to search, we know that sure enough, there's no, we haven't found the needle, right? So we can imagine one case that should be pretty easy to solve. So includes, and if we're looking for, our list is none, or the empty list, and we're looking for a needle like 210, right? We would expect that to result in a false value, right? We haven't found 210, and 210 is not included in the empty list none, right? And so we would think of this as a base case. And the strategy that we're learning here is to start by thinking about your base cases. Start with the simplest problems you can imagine. What are the ways that you know that you've sort of completed your job with the least amount of work possible? This is a very lazy approach to thinking about solving a problem, right? Well, yeah, of course, like this would be easy to implement. If you give me none, I'm going to give you back false, and my job is done. Well, what's the next most challenging list we could imagine solving? Or next most challenging haystack we can imagine. Let's say we're includes, and what about a list where the haystack that we're given is just the head node of some list, is going to be, say the node 210. And I'm just going to draw an arrow to nothing. We don't know what comes after this based on one invocation of this function, right? We're just given one node at a time, and we're going to be trying to think about one node at a time. That's going to be one of the key strategies involved in this process. And we're looking for 210. And this feels like a pretty easy solution too, right? Like, sure, you give me 210 as the first node in my haystack, and I'm going to give you back true, like, because that's what you're looking for. I know that we found it, right? So this would be another base case, right? We know exactly what to return. We can completely solve the problem that we were trying to solve at this point. There's not, I've seen enough, right? We don't have any more work to do. Well, what's the next most challenging thing we could do? So notice we're working our way from the simplest problem that we could solve to a slightly more challenging. And the key strategy we're going to employ here is, well, if we don't know how to solve the problem with the current position we're at in this list, we're going to do what we need to do with the current node and then leave the rest to recursion. We're going to say, recursive function calls, that's your problem to go worry about, right? And so if we imagine, okay, well, what about includes? And we're going to use, I'm just going to reference haystack as the variable that references, the node 110 haystack. And 210 is what we're looking for. And what is this going to result in? Well, we're going to be lazy here. We're going to say, you know what, we can't solve this, but we know that, the node you're looking for, the value you're looking for isn't the top of the haystack, isn't the head of the haystack. So, go do this again, but on the rest of the list, right? And go leave the rest to the recursion, right? We're gonna be lazy here and say, okay, well, maybe check the next list using the exact same the next value in the list using the exact same process. So includes, and then haystack.next. And I'm going to run out of space here. So I'm just going to wrap around and say haystack.next and 210, right? So check the rest of the list for the value 210. And this is our recursive case, right? So this is our recursive case. And if the next value is going to be 210, then we would return true. If it's going to be none, then we know we've reached the end of our list and our job is complete. Otherwise, if it's neither of those cases, if it's neither of our base cases, then we're going to try again on the next node, right? But notice we're sort of working our way from the back of the problem, from the simplest case possible towards the recursive case that's going to move through each item recursively. So now that we've got this general strategy down, let's try implementing this in some code. Right? So in VS Code, I've got the starting point, some of the starting code from our current exercise 6, where we're implementing some linked list algorithms. And I'm going to continue on in this file. And I would encourage you to go ahead and set up exercise 6 to be sure you're ready to start on it. And you can follow along with the video once you're there. If you otherwise want to just jot down this code in a Scratch file somewhere, that would be totally fine too. There's no more code than this for this particular exercise. So pause the video here and be ready to continue coding and resume once you're done. So let's take a look at what you're seeing here. This class node is a node in a linked list. It has two attributes, a data attribute that's storing the number of a node, and then next, which is importantly an optional next node, meaning it's either going to be a node or it's going to be none when we've reached the end of our list. We've got a constructor that we've talked through before, and then there's this magic method that's special because of these double underscores named REPL. And we're going to talk explicitly about REPL in a video coming up, right? But for now, I'm going to shorthand, leave it to the documentation to say this produces a string representation of a linked list. And we can get a feel for this in just a moment once we are testing our data out. But basically, it's going to automatically create a string representation of a linked list. So it's like 110 and then an arrow and then 210 and then an arrow and then none is what we would expect given our previous example. So let's go ahead and set up a skeleton for the function we're trying to implement. So def includes, and we have our haystack, which is a parameter. And what is the type of haystack going to be? Well, we need to be able to support an empty list, but we also need to be able to support, a node or some start of a node, some head. So we can use optional node as the parameter type. And we need the thing that we're looking for. That's going to be our needle, which is an integer. And this is a function that returns a Boolean value. And for documentation purposes, we might just write, okay, return, or let's just form this in terms of a question, because this is what we would call a predicate. Is needle included? Is needle in the haystack? Right. Okay, well, we've previously applied our new strategy and technique for solving a recursive function. So let's go take a look at what we had. We had a base case where if haystack is none, we're going to return false. All right, so let's go try and add that case to our code. So if haystack is none, we've reached the end of our list, so we can return false. Right, our job is done. There's no more for us to see here. Right? You didn't find what you were looking for in this list. Else, what we can do, and actually let's just do this as an elif. Elif haystack.data is equal to needle. Then what are we going to do? Well, this is the case where we found the needle in the haystack, right? And we're going to return true. Right? Finally, we have an else clause. And this is going to be our recursive case. So we've covered our two base cases, and we can remind ourselves of those really quickly. So we've covered the case where we found what we're looking for. That's the second base case. We found the case where we reached the end. We didn't find what we were looking for. That's the first base case. And now we're saying in the recursive case, well, we don't know. Let's leave the rest of the problem to the beauty of recursion to figure it out and process the rest of the list recursively by applying the same process recursively. All right, so let's try and express that in a little bit of Python code. Otherwise, we're going to return includes haystack.next, so process the next of the list, and with the same needle, right? And that's a pretty straight translation from trying to conceptualize a solution to this problem by working our way out from the back and by thinking about how we solve the simplest problem possible and then making it slightly more complex, slightly more complex. And so let's try this out, right? So I'm going to open up a REPL, and I'm going to say Python to start a REPL, and from, in my file is exercises.x6.linkedList, import, and I'm going to use the asterisk here to bring in all of the names, includes and node in one go. If we wanted to, I could, we could also do it like this, node and includes. But generally you can use the asterisk if you want to bring in all that matches all of the names in a given file. All right, so now if we wanted to, we can set up our list. So our courses are going to be a node, and the first node was 110, and it was followed by the next node is another node, which is 210. And that was followed by none, right? So that was the end of our list. So we've got two nodes. And when we evaluate this, if we say, well, what is courses? This is going to be where that repr method, that magic method comes to be. And we notice we get a really nice string representation, 110 followed by 210 followed by none. Okay. That's what we ultimately want to get to. But how might we test includes with something a little bit simpler and to test our base cases? Right, so maybe we try calling includes first with a haystack of none and a needle of 210, right? And this should hit our base case where haystack is none and return false. Sure enough, it does, right? We could try includes with the other base case where we have node of 210 followed by none and 210. And that's going to return true, just as we expected, right? So those are two simple cases. And the next thing we can test is includes courses of 110, right? So courses, remember, is 110 followed by 210 followed by none, and that worked. And that required the recursive step. We can make this list even longer if we wanted to test whether or not it works, but I assure you there's not many places for this solution to go wrong, and it won't. The other thing we could test is what about testing the other base case where what we're searching for doesn't exist. Oh, and I should have actually made this 210 here. So let's be sure. We matched 110, which was our first base case actually in courses, because that would have hit the elif before any recursive calls. But 210 means we can test the recursive step where it's going to have to recur once. Oop. And sure enough, it worked. I had too many parentheses when I tried to run it before. And then if we were to try includes courses and then something that doesn't exist, 999, that's when we would recur twice to hit the base case and return false, right? If we wanted to, we could just convince ourselves that this was working as we expected, and we could print, say, the needle each time our, let's print, the needle would be the same each time. Let's print haystack.data. So this would be like the first, actually, let's print haystack. Right? And this will tell us what is the list we're processing as we move through this problem, right? And so if we wanted to actually import this, we would need to quit out, start again, and from exercises.ex06.linked-list, import, I'm going to use the star here and be lazy. And now I could say includes, and I'll just write out these courses directly. So 110, node 210, followed by none. And 1 parenthesis match, 2 parentheses match. All right, we're good. And then we're searching for, say, 210. And notice that the haystack, when the first recursive function call to includes, or when the first call to includes was made, this wasn't a recursive call, it's 110. And then in the first recursive call, it's 210, and that ultimately evaluated to true. But if we tried searching for something that didn't exist, like 9999, you'll notice that we search through the haystack where we are given the 110. And then the next time includes is called the head node, or the haystack is a node that's 210. And then the last time it's none. So we're moving one by one through each node in our list, right? And so the general strategy here, that is the important takeaway in this mode of thinking, is to try and make your life easy, right? Get some easy wins in the bag. Get your base cases figured out first. And then once you have your base cases, you want to think about, well, what's the smallest step I can take from where a base case is to working towards a base case in a recursive step, right? And this is actually great life advice too. Like, get some easy wins first before you try and come up with a complete solution to a really difficult problem. Try and solve the easiest cases before you worry about all the complexities that might happen otherwise. And the really neat thing about recursion, when you start becoming more comfortable thinking in this way, is that you'll realize that many times the recursive solution to a problem can be very simple and beautiful. And once you see it, it's like, wow, how did I not recognize when I first started looking at this problem that there would be something, such a simple solution to it. But it takes practice, and it takes getting comfortable with thinking about the problem from the back end first, rather than the very start of it. And hopefully with this one cool trick, some of these solutions to the recursive problems that you're trying to solve will be much easier to attack from the back to the front.